Hello everyone. So this is a short video today about the conservation of momentum, and we're going to try and cover it in a way which explains where it comes from some ideas you already know about Newton's laws. So we begin with the simple thing. We have two particles traveling towards each other with different velocities, v1 and v2, and we think about them at some time ti, the initial time. If they have masses m1 and m2 and their velocities are given by these functions v1 at ti and v2 at ti, then we can write down, of course, their momentum at that moment. Now, the thing which you'll be used to doing is to then consider some time later, we'll call that t final, after the elastic collision of these particles, and we can similarly write down what the momentum of the two particles is at that point. Conservation, of course, means that the sum of those momenta are conserved. But where does this really come from? Well, let's just consider one of the particles for a moment. Okay, we'll consider this the M1 particle, and so this is just the same sort of system we had before. What can we write down for this? Well, we can write down the change in momentum from before and after the collision. So this is the delta P1, which is equal to the P1 at T final minus P1 at Ti. You may have written this before as P1F or something like this. This notation just means take it to be at that time. We're going to make it a function of time for now. Okay, well, we just plug that in, and we end up with this relation. And then, again, we can define a change in velocity or speed for this object, as we're only sort of considering one direction here, the x direction, if you like. And so that's what the change of momentum for that particle is. Okay, now we can do something which is slightly different. We can now multiply this by delta t and divide by delta t. Why might we want to do this? Well, you'll notice we now have a delta v1 over a delta t, which, if you think about it, is a kind of acceleration. So this is the change in velocity of the particle in some period delta t, which is exactly an acceleration. So now what we have is the change of a momentum, the delta P1, is equal to the mass of the particle times the acceleration of the particle during that interaction times this delta t. Okay, why are we doing this? Well, you'll notice m1 times a1, this is just, of course, the force applied to the particle. So the change in momentum is just the force times the time period over which that force is applied. So one thing to be careful of here is we were a little bit lax in when we defined what this Ti and Tf are. Of course, they can't just be any times. In general, momentum must be conserved between any 2 points. What we really mean here is the initial moment when the force begins to act to the final moment when the force acts. Let's think about this in a little bit more detail. Exactly what do we mean? Well, here we have the two particles again, and we can imagine them incoming to each other and colliding. As soon as they touch, they'll start to apply a force to each other. So in fact, we have a force of m1 on m2, that would be F2, that will act on m2, of course, and we'll also have an equal and opposite force of m2 on m1. So it's really this time period during which they are colliding which we're interested in, and that's what the delta t is of interest. Okay, after they collide like this, they'll, of course, in this case, they both turn around, and they then move in opposite directions to each other in the usual way. Okay, let's think a little bit more about what happens during the interaction. So we already had this equation, so this was from 2 slides ago. We had this change of momentum is equal to the force times that time period over which it acts. We can rearrange this, and we can say that the force is equal to the change of momentum divided by that time period. Now what happens if we just consider a very, very small moment in time, an infinitesimal amount of time? Or we can turn this into its differential form, which says that the force 1 acting at that time is the derivative of the momentum. So here the d by dt is acting on P1 of t. Okay, what's the idea with this? Well, P1, of course, is just the mass of the particle times the speed of the particle. Well, the mass of the particle remains constant, at least in this example, and so we can just pull that out the front. Its time derivative is comes out of the time derivative, and so we have m1 times d by dt of v1. And what exactly is that? Well, of course, that's just the acceleration. So we have, again, we've come full circle. The force is equal to the mass times the acceleration. Hopefully this helps to sort of understand that this whole idea is sort of logically complete. They all come from these Newton's laws. So this is, of course, just Newton's second law. Okay, what's the importance of this? Well, we've already used Newton's second law to see where that momentum equals mass times velocity comes from. But now we can use Newton's third law to try and understand the conservation of momentum. What do I mean by that? Well, Newton's third law, in this instance, just says that the force, the F1 force, which was acting on particle 1 from 2, is equal and opposite to the force applied to particle 2 from 1. That just means that F1 of t is equal to minus F2 of t in this instance. Okay, well, we also have some nice relations for what these F1 and F2 are. So previously I've done everything in terms of the first particle, but we could equally have done the same thing with the second particle, and then we'd be able to write down these two relations. So on the left-hand side is just what we had a moment ago, and on the right-hand side, as I say, is what you would get for the second particle. Okay, now we play a slightly different game, sorry. We move the derivative of the momentum on the right-hand side over to the left-hand side. Okay, now we have a derivative plus another derivative of something else, and those two derivatives are both of time. So what we can do is we can factorize this as such. So we have the differential with respect to time of the sum of the momentum, and that thing is equal to 0. So notice this has come directly from Newton's third law. What does it mean if the differential of something is equal to 0? Well, it means that that thing must be a constant. So the sum of the momentum of P1 plus P2 must be equal to a constant. What's the application of this? Well, what you'll notice is here we didn't ever have to specify which time we were talking about. It could be that initial time, it could be the final time, or it could be some time in between. What that means is that we can pick any two moments in time, the initial and final time seems quite convenient, and we can write down this equation. Since it always has to be equal to a constant, it always has to be equal to the same constant, and therefore P1 at Ti plus P2 at Tf must be equal to, P1 at Ti plus P2 at Ti must be equal to P1 at Tf plus P2 at Tf. Now this is the usual conservation of momentum equation which you're used to using and just pulling out and applying. And so in the usual way, you'll then write down something like this, and if someone asks you to solve for the velocity of one of the particles at the end, you'll be able to do so. But this is really where it comes from. It's a statement about Newton's third law and the relation between momentum and Newton's second law.